today is Valentine's Day, but some students here or some people are new in this seminar on February 14. For us, it's a special day because it's the birthday of Dr. Ayman.
Oh, thank you.
We wish you all a happy birthday and long life filled with joy, happiness, and excellent health.
Thank you, Kristen.
So the seminar usually takes place Tuesday, but when you have a special day, it doesn't matter the day of the week. February 14 is the day of Dr. Ayman talk. So his talk is on amazing numbers, so clearly it will be an amazing talk. So please, you have the floor.
Thank you, Kristen. Yeah, this is like a tradition as every year at this time. Oh, yeah, every year at this time I give a talk, and I think one of the talk it was I think my first talk in the sequence. It was 2 or 3 years ago about number 9.
Yes.
So I'm not going to talk about that anymore. So I'm going to talk about other numbers that I find them amazing, and maybe you will too. First thing, let me remind you with what we mean with a prime number. A prime number, you know, it's a whole number, integer, and the only factors are what? One and itself. And we always start from number 2. 1 is not a prime. So the first prime number is 2. Okay, let me give you something about prime numbers. Like, choose any prime number you want. Let me draw that in front of you. Okay? P is a prime. So let's call this is B and this is C. I want this prime less than B less than C. Okay? So B prime, this will be fixed. B and C, I want them to be integers. B and C, I want them to be integers. And all of us know that, you know, that C squared equal B squared plus So when I fix a prime, the question, how many integers can I find where B less than C and satisfy this? So the question we know, is it true for every prime? Can I find? Okay, the first thing, what this being a prime special, give me a prime number, then there is only one and only one B whole integer, and only one and one C whole integer. Remember, B and C, I want them to be integers, where this is not just that. Also, if this is correct, I know that C has to be B plus 1. Okay, let's practice. Let's give me a prime, like 7. So I need to find B and C. And I told you there is only one B and one C that satisfy this, only one, where B and C are, can you guess?
It's a 3, 4, and 5.
Well, my P is 7. I selected. So this is 7. So I need B and C, where B has to be bigger than P, and C, you see that? P less than B less than C. Can you guess what should be B and C? And I'm telling you, there is only one B and one C. And this is true for every prime. Give me any prime, then I can give you B and C. Okay, This is not difficult, really. Maybe some of you seen that. But I try, if you have a calculator, read a calculator. Let's take B to be 24 and C to be 25. Check on your calculator, is it 7 squared plus 24 squared equal 25 squared? Is it? Yes. Now, if you spend your life and the life after, try to find another two whole numbers, there is no such. You can find many, infinitely many numbers, but remember that B and C are integers. Okay, so the prime numbers here kind of unique. Like if I put 9 here instead of P, and I ask the question, yes, I can find B and C, but not unique. I can give you 2 or 3 different solutions for B and C. But for this to be prime, such B and C are unique. And this is how, and look at the difference between B and C is 1. Is 1. Okay, let's take bigger than that. Let's take P equal 11. Can you try again? Maybe you see the trick. P is 11. So I need to find B and C, satisfy that. B and C are integers, and B has to be bigger than 11, and C bigger than 11. Can you guess? 60, 61. B equals 60, C equals 61. And these are the only solution. Okay, I will tell you how you do it in general. In general, if you choose a prime, P, you select P. Then you take B to be P squared minus 1 over 2. It's not difficult. C equal P squared plus 1 over 2. Of course, here P is what? Bigger than 2. You start from 3 because this will not be integer if P is 2. Okay? So your prime bigger than 2. So that's a general formula. And the question, this is the only solution. You cannot come up with any other solutions. Okay, so this is one thing about property of a prime number being the base and the triangle. And can we find integers? Yes, and these integers are unique. If I change this into some other number, maybe you can, but you will lose uniqueness. Maybe you will have many choices for B and C. Not many, still finitely many. Okay. The other thing I want to tell you, which is kind of amazing, all of us know, how many prime numbers are there? Infinitely many. Okay? Keep this in mind. We have infinitely many prime numbers. And even in a course in discrete math, the two-line proof, you prove using the unique factorization, you can prove that theorem. It's not difficult to prove. Okay, but now choose any number you want, as big as you want. 10. I don't know what this number. I mean, it can even choose bigger than that. Okay, keep in mind we have infinitely many prime numbers. I'm telling you, there exists an integer, K, where all, let's call this, how much is that? Let's call it M. All consecutive odd numbers. So how many are we gonna count? M. all the next m consecutive odd numbers, none of them is a prime. Look, we have, like if I choose a million, choose 1,000, there is an integer k, where k plus 3, k plus 5, k plus, then a like 999, all the odd numbers. None of these are a prime. None of them consecutive. So look at the huge between what? The gap between the prime numbers. So if I choose a million, there is a number. I can start from that number. All the consecutive 1 million number, none of them is a prime. At the same time, we have infinitely many prime numbers. I think this is amazing. In a way, if you think it in here, in fact, I cannot tell you here how you find, like if you want to choose 1,000, choose this number, 2,000 factorial, that's a number. Now, this is definitely not the prime. Add 3. This is not the prime because you can factor 3. This is 2,000 factorial, right? And you see that trick. So it's not difficult to see even, plus 5. This is the next one is this number. They are consecutive odd. I can factor 5. So this is not the prime, this is not the prime. Keep going. 2,000 plus like 9, whatever, 1,099. In a way. Maybe you need to fix that in a way. But anyway, all these consecutive odd numbers, none of them is a prime. None of them. So imagine if you choose a trillion, you can start from 2 trillion factorial, and then plus 3, plus 5, plus 7. Keep going. You will construct a trillion odd numbers. None of them is a prime, and they are consecutive. Okay, why did I mention that? This is crucial for the next one. How many of you heard of Mersenne? Or I'm not sure about the name. I will write it down. Mersenne prime. Mersenne prime. This is kind of, anybody heard about Mersenne prime? Okay, so let me tell you what's Mersenne prime. Let's start with 2. N equal 2. What is 2 squared minus 1? Is it a prime or not? Is it? Okay, let's start with n equal 3. 2 cubed minus 1. Prime. Right? Okay, what about 5? So you see, I'm taking a prime numbers. Start from 2, 3, 5. What is 2 to the 5 minus 1? 31. Is it a prime? Yes. Okay, n equals 7. 2 to the 7 minus 1. What is that? It will be prime. Okay. Oh, this seems wonderful. What's the next prime? I mean, what's the next after 7? 2 to the 11 minus 1 is not the prime. Whoops. 2 to the 11, if you have a calculator, Try 2 to the 11 minus 1, and you see you can factor it. So this one is not a prime. So what you discover that 2 to the, here is what he said, which is true. Look, if 2 to the n minus 1 is a prime, then n, this is easy, high school math, n must be a prime. It's not difficult. If n is not a prime, then you can write it and you can factor this number. If 2 to the n is a prime, then n must be prime. So you know that 2 to the 8 minus 1, 2 to the 9 minus 1, 2 to the 10 minus 1, these are not prime, because if this is a prime, then n has to be prime. But the converse need not be true. What is the converse? If n is a prime, then 2 to the n minus 1 is here.
This could be anything.
Yeah, here, fail here, right? Because n equal 11 is a prime. 2 to the 11 minus 1. Okay, try 2 to the 13 minus 1 will be prime. 2 to the 13 minus 1 will be prime. Why am I mentioning that? This prime called what? Mersenne or Mersenne, maybe, is that French? Is that from Marseille?
No.
Oh, okay. Mersenne prime. Till this minute, it's still unknown how many Mersenne prime are there. Not just that, we don't know whether there are finitely many or what? Infinitely many. I mean, till this minute, we don't know how many Mersenne prime are there. And we don't have an answer to whether they are finitely many or infinitely many. Okay, and this is developed school of research. They start a method called the locus-Lemur test to test if the number is Mersenne prime or not. You'll be amazed now. How many Mersenne prime are known? Maybe there are 6 or 7 or 8 in the first 100. Because, 3 is okay, 5 okay, 7 okay, 13 okay, 19 will be okay, 23 no, 2 to the 23 minus 1 is not, 2 to the 29 no. I think 31 will work. Guess what? We only know 51 Mersenne prime numbers.
What's the largest one?
I'll tell you now, we only know 51 Mersenne prime numbers. And this is where the use of technology comes. I remember when I look at this problem in the 80s and the 90s, the number, they were like 24, 27. But after 2000, we have a huge machine and this machine will help us to discover, because you can make tests whether this is a prime or not, Here is the number. This is in October 2020, recent. The biggest Mersenne prime number is 282,589,933 minus 1. This will be prime number. 2 to this number minus 1, that will be prime. And this is this is the number 51. Okay, you should not be, and why did I do about the gap at the beginning? Because you should not be amazed. I mean, it is amazing because remember the gap between prime numbers is amazing. So I'm not so surprised. And this is in 2020. And of course, are there any more Mersenne prime?
How do you prove that?
Well, here's the thing. We don't have a proof. The machine will help us to discover if there are what?
Factors.
More. Right? But if the machine does not give us more, that does not mean we don't have any more. Because the gap between the prime numbers is what? It's a huge. I mean, look, this is, of course, this is not by calculator or my laptop, very high computational. In fact, the person who discovered this number is an electrical engineer. He's not a mathematician. And they formed a Mersenne prime web page exchange. I mean, it's like a school become of people who, if you hear about UFO, they search on to meet, if there is another life somewhere. These people, what they do, they work a lot of hours trying to find what is the next Mersenne prime. Because look, this is very huge number. Very huge number. Okay? So this is amazing to me when I think about it, that till this now, we only know 51 Mersenne prime numbers, only. And this is the largest one. And this is in 2020. Okay, even more interesting is this. Can you wake up? Okay, I want to give you the number 6. Yeah. Can you please find all factors of 6? Can you give me all factors?
So 6, 3, 2, and 1.
Okay, remove 6, the proper one.
Okay, 3, 2, and 1.
1,
2, and 3.
add them.
6.
6. So if you add the proper divisor of 6, you come up. Okay, what about 8? Is it true? Like if you take 1, 2, and 4. If you add them, you get what?
7.
7, which is not?
It's not 8.
8, right? Okay. What about 28? So number 6 is okay. What about 28? The proper divisor. 1, 2, 4, 7.
14.
Can you please add?
This one is true.
It's true. A number with these properties, we call it perfect number. Okay, I'm gonna tell you how this is related to what?
So then we're saying prime.
Mersenne prime. If you answer one of them, you answer the second one. Till this minute, we don't know how many perfect integers are there. Till this minute, we don't know how many perfect integers. Like 6 is okay, 28 is okay. And I can tell you, if you try to, I don't know, 31, if you want to multiply it with 8, what you come up with? 31 with 8. 248. 248. If you take all the proper divisor, they will add up to what? To 248. So this is perfect. So what is a perfect integer? If you add the proper divisor, you come up with what? Okay, look at this result, how this is connected. N is perfect. if and only if n is equal to p minus 2 times 2 to the p minus 1, such that p is prime and 2 to the p minus 1 is a prime. Well, remember what? If 2 to the p minus 1 is a prime, what we call this? Mersenne prime. So if you have a Mersenne prime and then you multiply it with what? With 2 to the p minus 2, you always come up with a perfect number. So a perfect number has to look like that. But for God's sake, how many Mersenne prime number do we know? Only 51.
And we only know 51
Perfect numbers. So if you answer one of these questions, like if you answer there are infinitely many perfect numbers, then you will answer the question, there are many infinitely many Mersenne. So the perfect integers and Mersenne prime are connected. And if you know the answer for one, then you know the answer for the second. Yes?
Are Mersenne primes always twin primes?
Huh?
Are Mersenne primes always twin primes?
Twin?
Yeah, so like 5 and 7. Or 3,
No,
7,
no,
yeah.
because look, the gap between them is huge. Like you have 2 to the 19 minus 1 is 23 is not the next prime. Yeah, I see what you mean. In fact, if they are a twin, then maybe we will have more. But that's not. And when you look at that and you put it in your head, you will be really amazed how much is that thing. Okay, that's enough about prime numbers. So I told you how these are connected. And if some of you, a student, are engineer, maybe, I don't know, maybe if you have computer skills, you can join that group, because they established like a research group looking for Mersenne prime. And these things are kind of, and I find them very, very interesting and unique. Okay, the other one I want to talk about that will really amazing for me, these two primes. Why they are amazing and they are unique? Okay, I want to ask you, carry 37 in front of a mirror and read what you read.
Are they the only mirrored primes?
One by one. 37, I carry it in front of a mirror. What you gonna read? What number?
73.
73, right? Is it? Or if you carry 73, I put number 73 in front of a mirror. What you gonna read? 37. Okay. Watch. 37, 73. So they are the mirror of each other. You agree? The mirror of each other. Okay. This is a prime, and this is prime. Maybe that's also okay, because you can tell me 91 is 91 prime. What is the mirror? 19. Are they prime?
Yes.
So there is nothing unique about what? These two, but I'm going to tell you more. Let's start counting the prime numbers starting from 2. So we have 2 and the second prime,
Right.
and
Five.
when you reach 37 in the list, this will be the 12th prime number. On the list, when you start counting, this is the first prime, second. 37 will be what? What is is the mirror of 12? It will be this number. This is what makes them unique. They are the mirror prime. One of them in the list 12, the mirror 21 will give you, and these are the only two prime numbers with these property. There is no any other prime number, only 37 and 73. They are the mirror of themselves, and the rank, when you put them in the list, one of them is 12, the mirror of 12 is 21st. Okay? So this is also a second kind of interesting property. I have another three. I will end up, I'm not going to keep you for long. All of you heard of the golden ratio. Yeah, so this is nothing, but I think not many heard of this number. Why it is so amazing. This is my last one. Take the number 6174. This is a very amazing number. Why? Why this is so amazing? I need a calculator. You have a calculator. Okay. Give me any 4-digit number. At least 2 digits are different. At least 2. Give me just 4-digit number with at least 2 digits different. Can you?
9566.
Huh? 9?
566.
Okay, that's the number he selected. So I have these 2 digits are what? Different. Okay. Take this number as write the digit in ascending order. Go ahead. Ascending.
5669.
For ascending, let's see descending first.
9665.
9.
665.
Okay. Ascending.
5669.
On your calculator, do the minus.
3996.
3.
996.
Okay. Let's repeat. Here is the one. What I'm gonna do, repeat this step. What you're gonna arrange in descending, and then, okay, so how you gonna, what this number will be?
996.
9963 minus 3699. What's the answer?
6264.
6264. Okay, let's repeat. 6642, right? Minus 2466.
4176.
4176.
76.
Okay, let's again. What you're gonna do? 7, 6. Make sure you do it correct. 4, 1 minus 1, 4, 6, 7. Right?
6174.
6, 1.
74.
Now try again. What you get?
617. It's the same.
Huh?
It's the same result.
So you so now if I repeat 6174 minus what? Sorry, I'm gonna do 7614 minus 1467. What that will give you?
6174. You're stuck in a loop.
Step. I don't care which number you start with.
You end up
You always end up here. Always. This operation will be terminated when you reach here, you're done. So you take a number, at least 2 digit, Of course, it has a mathematical, but it's not, maybe if you are good and sit down, maybe you see why. But that's what makes this number so unique. 6174. Take any 4-digit number with at least 2 different, do from the biggest to the smallest, and then from the smallest to the biggest, and keep repeating. This process will be terminated, and it will be terminated at what? Always at this number. At this number. Okay? All right. So we talk about prime, we talk about Mersenne, and we talk about perfect. These are amazing numbers, and this number is amazing. And the other amazing number is 9, which we already talked about it. It was the whole lecture, I remember. Isam was there for number 9. Maybe I should stop, and I thank you. I mean, the goal of the today talk is just, entertain you. I hope I succeeded in the entertainment. It's not like, but it's kind of, I think all of you agree, kind of interesting. I mean, why these things, especially the Mersenne? I mean, this is for me like.
So with
with
these
all
single machines, I mean, you just simply can run the machine and let it do the testing for you, 2 to the power n minus 1 prime or not. So is there?
But here's the thing, as I said, there is a school of.
Do we know up to what point they start?
Yeah, there is, in doing that, they develop an algorithm, they call it locus linear test method. Of course, they are not gonna, to test for this. Well, I mean, I see, because this will keep going forever, even whatever. So, and that's where there is some research. It's not just let the machine do it. The machine cannot do it up to certain, and then, I don't care. But they are developed some method. I mean, this problem of the Mersenne, it seems like established a new school in a way, because there are some people, their job is just looking for what is the next one. And they are working, and as I told you, the recent one is 2020, and it's still going on. And I think before 2020, it was 2012 or 13, the number before. Imagine the gap in years before they discover the next one. Okay, thank you for coming, and have a good day, all of you.
Thank you.